Hello dear students, welcome to Biochemistry by Revati. I am Revati, and in today's class we will learn the structure of monosaccharides focusing on Fischer and Haworth projection. Okay, let's get started. Coming to monosaccharides, you have already learned about monosaccharides, right? What are monosaccharides? Mono means single, means one sugar unit. They are the simplest form of carbohydrates, isn't it? They cannot be further hydrolyzed or broken down. Often referred to as building blocks of all carbohydrates. If you see the general structure of monosaccharides, they contain a carbon chain with either aldehyde group or ketone group. Okay. So monosaccharides contain a carbon chain with either an aldehyde group or a ketone group, right? If the carbonyl group is CHO, then it is aldehyde. Means when it is aldehyde, then the sugar is called as aldose. If the carbonyl group is ketone group, then the sugar is called as ketose. Okay, and it also contains multiple hydroxyl groups that are attached to the carbon atom. Okay, they usually have the formula CH2O whole to the power of n. So here n is the number of atoms. So it will be generally 3 to 7. Is it clear? Now let's learn the structures of monosaccharides. First, we'll start with n with 3 number. So n is equal to 3 means substitute these 3. CH2O whole to the power of n means 3. So you'll get what? C3, 2 into 3, 6. CH6 and O3. So now when n contains 3 means when the carbon contains 3 atoms, then the sugar is called as triose. Triose means 3 carbons. Okay. Now let's say with example, triose is glyceraldehyde. So if you start numbering the carbon atoms, carbon 1, carbon 2, and carbon 3. So it is an example for triose, right? Now this sugar is called as glyceraldehyde. Why? Because here the carbonyl group is what? Aldehyde group. Is it clear? So now this is an example for aldose because it contains aldehyde group. So the example is here what? Glyceraldehyde. Let's see for ketose group. It is dihydroxyacetone. What is the sugar called as? Trihydroxyacetone. Start numbering the carbon atoms. Carbon 1, carbon 2, carbon 3. So it is also a triose, means 3 carbon sugar. Okay, but there is a difference between glyceraldehyde and dihydroxyacetone, because here the carbonyl group is ketone. We have already discussed, right? If the carbonyl group is ketone, then it is present at second carbon atom. If the carbonyl group is aldehyde, then it is present at endmost, means first carbon atom. Now it is an example for ketose. Is it clear? Now let's see for N is equal to 4, means what is the sugar called as? It is tetrose. Before we have seen triose, right? Let's see. So you'll get C4H8O4. Is it clear? So now here I'll take example as erythrose. Let's see the structure. Start numbering the carbon atoms 1, 2, 3, 4. Now here it contains 4 carbon units. Is it clear? So here again it contains aldehyde group, means it is an example of aldose. Let's see for ketose. The example is erythrulose. Same, here it is ketone group. So it is an example for ketose. Is it clear? Now let's see for pentose. Pentose means what? Pentose. Pent, carbon, 5 carbon atoms. So if we take N is equal to 5, substituting in the formula, 5 means C5H10 and O5. Now here I take example as ribose. Let's see the structure. Start numbering 1, 2, 3, 4, 5. Now it contains 5 carbon atoms, so it is a example for pentose. Again, the carbonyl group contains aldehyde, so it is an example of aldose. Next, ribulose. Now let's see this structure. Start numbering 5 carbon atoms, and the carbonyl group is ketone group, so it is an example for ketose. Is it clear? Now in the same way, again we have to check for number of carbon atoms as 6, means the sugar is hexose. So following the formula CH2O whole to the power of n, substituting the n value as 6, you will get C6H12 and O6. And the most common example we have already learned in even in the previous classes also, right? So that's the example is glucose. So here glucose is the 6 carbon compound. It comes under hexose. Let's see the structure. Start numbering 6 carbon atoms. So it is an example of hexose. And the carbonyl group contain aldehyde. It's an example of aldose. In the same way, let's see for ketose. The example is fructose. Structure as start numbering 6 carbon atoms. So it is an example for ketose. Here carbonyl group is ketone. Now let's see the final based upon carbon atoms, that is N is equal to 7 means heptose. So substituting in the general formula, we'll get C7 H14 O7, and here the example is D-glycero D-mano heptose. Let's see the structure. Start numbering 7 carbon compound. Again, carbonyl contain aldehyde, so it is an example of a aldose. In the same way, let's see for ketose. Example is pseudoheptulose. Start numbering. So again it is also 7 carbon atom, and here the carbonyl group is ketone group. So it is an example for ketose. So these are the structures that we have discussed from N is equal to carbon atom 3 to 7 means triose to heptose. In solutions, monosaccharides can exist in straight chain structures, okay, and the carbon atoms are numbered from starting the carbon and the carbonyl group. So here in glucose, C1 is the aldehyde carbon, and in fructose, C2 is the ketone carbon. But remember, in water, monosaccharides cannot be stable. They cannot be stable. Most sugars prefer ring structure only. About this we'll discuss. Okay. Now let's discuss about Fischer projections. These projections are first introduced by German chemist Emil Fischer in 1891 to simplify representation of 3D organic molecules. Okay, especially carbohydrates. Now what is this Fischer projection? It is a 2D representation of 3D structures. Now what contains in this Fischer projections? It contains vertical lines. Here the bonds are represented. Here the vertical lines show the bonds that are moving away from us, and the horizontal line represent the bonds coming towards us. And here the carbonyl group is always present at the top position. Either it may be aldehyde or ketone. And the hydroxyl groups are present left or right depending upon the position. Let's see with an example of glucose. Now you already know that glucose is a 6-carbon compound, and its formula is C6H12O6. Aldehyde, OH, H, H, HO, OH, OH, 1, 2, 3, 4, 5, 6. So now this vertical line represents the bonds moving away from us, and this horizontal line represents the bonds coming towards us, right? Now this is a structure of D-glucose. If you see the last second carbon atom, last means from the last, this is the second carbon atom. Now there will be a difference in this configuration. For L, let's see. Now it is a L-glucose form. See here, D and L forms are mirror images. Now whatever the positions of hydrogen and hydroxyl groups present in the D form are opposite in the L form. But the specific difference is the second last carbon configuration will be difference. OH, if it is the OH is on the right, it is D-glucose. If it is on the left, it is L-glucose. So here D and L forms are the stereoisomers. Means they have the same chemical formula, but the arrangement of atoms are different. Is it clear? Now let's learn about Haworth projections. Okay, here the monosaccharides exist in the cyclic form in aqueous solutions, and this is shown by this Haworth projections only. Okay, now this is a simple way to draw ring structures. And here the carbonyl group. Carbonyl group means whether it may be a aldehyde or keto group that will combines with or reacts with, it will react with hydroxyl group to form what? Hemiacetal in aldosis or hemiketal in ketosis. Now that leads to the ring closure forming 6-membered rings. Now these are called as pyranos. Example, glucose, and also leads to 5-membered rings called as furanose. Example, fructose. Is it clear? Now the rules to draw Haworth projections. First, the groups on the right, means in the Fischer projection, they appear down in Haworth projection. And the groups on the left in the Fischer projection, they appear up or first in the Haworth projection. Okay, then after ring closure, a new carbon called anomeric carbon is formed based on the hydroxyl group position. It is called as alpha and beta forms. Let's see. If the OH group is down, then it is alpha form. If the OH group is up, then it is beta form. Is it clear? Structure. I'm taking example as glucose. You all know that glucose is a 6-carbon compound. Now I'm writing the Fischer projection. Okay, structure. So this is the Fischer projection of glucose. Now here the carbonyl group, means aldehyde group, it reacts with the hydroxyl group to form what? Hemiacetal. Now what will happen? It leads to the cyclization. So this aldehyde group here, now whatever the groups which are present, means which are placed on the right, will appear down, okay, and the left up. You're getting or not? Now here the OH, here the OH hydroxyl group is present, right? Now there will be a proton transfer takes place. So after that ring closure will taking place. Let's see. After the transfer of proton, you will get OH here. Now this is a 6-membered ring. We call it as pyranose. Okay. So here what will happen? Here there is a transfer of proton leading to the new carbon as a anomeric carbon. Now this carbon will become anomeric carbon. Okay. Now if the hydroxyl group on the anomeric carbon If it is present down, then it is alpha, means alpha form. Now it is alpha D glucose. If there is a position or change of position, here if the OH is down, we call it as alpha D glucose. If the OH is up, then it is beta D glucose. Is it clear? Writing the Fischer projection, formation of semi-acetal, how the ring closure takes place, and how the anomeric carbons alpha and beta forms are formed. Is it clear? That's all for today's video. I hope you have understood the concept clearly. If you have any doubts regarding the concept, please comment on your doubts, okay? And if you found this video helpful, please like, share, and subscribe to Biochemistry by Revati for more simple and clear explanations, okay? And in the next video, we will learn the reactions of monosaccharides. Until then, keep learning and stay curious. See you in the next class.